Hello, today we're going to talk about molecular geometries, and I'm actually going to start in a simulation that we're going to use in class, but I think it makes it a little bit easier to see the shapes in 3 dimensions. Here we have the PHET molecule geometry simulation, or molecule shapes simulation, which you're going to use in class, and it has an atom in the middle, and then we can add bonds or non-bonded or lone pairs of electrons. All right, so the whole basis for molecule geometries is that electrons have negative charges and want to be far apart in space. So if I just add pairs of electrons here, you can see that when I do that, they end up as far away from each other as they can be, okay? And then if I add another one and another one, right, the shape we get is based on getting those electron pairs as far away from each other as we can because they repel. Remember, like charges repel. All right, so if we, instead of adding lone pairs of electrons, add bonds, remember all of our bonds, single bonds, have 2 electrons in them. So if we add just one other thing, it obviously makes a line. The name for that is linear. Okay. If we add 2 things, the farthest apart those 2 things can be from each other is 180 degrees. So we're still at linear. Okay. If we add a third thing, now the farthest apart those 3 things can get is 120 degrees. But you can see it's still flat. Okay. So it basically, makes like a triangle, but all of the atoms are in the same plane, and they're all 120 degrees apart. Okay, if one of those things is a lone pair instead of a bond, so if we take a bond away and put in a lone pair instead, we still get a bond angle of 120 degrees, and our electron geometry is still trigonal planar. Trigonal meaning it's all in a triangle, and planar meaning it's all in the same plane. But you can see the molecule geometry is different, and that's because what we see are the masses of the nuclei, okay? So if one of those electron groups is just a lone pair of electrons, then it's going to cause repulsion and influence the shape, but since we can't see it because there's no nucleus there, we ignore it when we're naming the shape. So when we just have 3 atoms at an angle to each other, we call that bent, all right? So now let's take the lone pair away and put our bond back. All right, and then look at what it looks like if we add a 4th. Okay, so if we add 4, now you can see we are no longer in one plane, okay? So if you look at it from overhead, you might think, oh, it looks kind of like a square, right? But it isn't. If they were all in a square flat, that would be 90 degrees. So 109.5, which is the bond angle for tetrahedral, is going to be larger, and that will allow our electron groups a little bit more space and reduce repulsion. Okay, so this shape is called tetrahedral, right? If you remember, tetra was 4 in our prefixes, and the shape that you would get if you connected all of the atoms on the outside is called a tetrahedron, so that's where the name comes from, right? If instead of a bond, we have a lone pair, we're still going to have a tetrahedral electron geometry, but now you can see that the molecule geometry has changed. We only have 3 atoms around that central atom, so it's going to be trigonal because it kind of makes a triangle, but it's not flat anymore, right? Because that extra lone pair on the top is going to force the atoms down out of the plane. So we get almost like a tripod, right? And this shape is called trigonal pyramidal or pyramidal. Okay, because you basically, if you were to connect all of those, you would get a pyramid with 3 sides. All right, if we take away another bond and add an additional lone pair, now we still have 4 electron groups. Our electron geometry is still going to be tetrahedral, and that bond angle is still 109.5, but if we ignore the electrons, which we wouldn't be able to see because there's no nucleus there, we get that bent shape again, but you can see that when there are 4 groups instead of 3, the angle reduces to 109.5 instead of 120. Okay, so that's just a summary of the shapes, and now we're going to go through some examples for how you would be able to identify them based on the Lewis structure. So first, just let's summarize what we just went over in terms of electron group geometry. So what I showed you in the simulation is that if we have 2 electron groups, you get a linear shape. The angle is 180, and if we were to draw a sketch of that, which is how you'll represent the shapes, it would just be 3 atoms in a line. And those could just be circles to represent the atoms, or could be the it's symbols for the elements themselves. And if we have 3 electron groups, that is trigonal planar. The angle is 120 degrees, and this is basically how you would draw it, all right? And then last but not least, if we have 4 electron groups, that is called tetrahedral. The angle is 109.5. That's the only one that's kind of weird to remember. And then drawing this one is going to be a little bit different because it's not in the plane, so we can't use only lines. All right, so to draw this one, 3 of the atoms can be in the plane at the same time. But if you do that, one of them will be sticking out at you, and we use this wedge to show that it's coming out of the board or out of the plane of your paper. And then the dashes show that it's going back into the plane of your paper. So each of these would then be not in the plane, and that shows the 3-dimensional nature. So you cannot draw tetrahedral with all solid lines. You have to use the wedge and the dash in order to appropriately show the shape. Okay, so now let's take a look at how this changes as we add or remove electron groups. One of our electron groups is not a bond, but is instead a lone pair. We go from trigonal planar to bent, right? And if we have a tetrahedral geometry and we substitute a lone pair for one of the bonds, we get trigonal pyramidal, right? And then if we substitute 2, we'll get bent. All right, so that just summarizes the relationship there, which we talked about before. So now let's go ahead and talk about how we can get that information from the Lewis structure. All right, so this is a great opportunity for you to pause and make sure you can draw the Lewis structures before we move on. So it's just a review of what we did in the last lesson. So CO2 looks like this after we draw the Lewis structure. That means there are 2 electron groups, okay? And 2 electron groups means linear, right? There are no lone pairs on the carbon. So that one is linear. Now it's pretty straightforward. Okay, next we have H2CO, all right? So we have the carbon in the middle, a double bonded oxygen, a hydrogen, and a hydrogen, okay? So it's important to note that a double bond is just 1 electron group. Just because there's 2 bonds, it doesn't make it a bigger group. It's just 1 electron group sticking off the atom. So this one has 3 electron groups, right? So the geometry will be trigonal planar, right? So it'll be that triangle shape that's flat that we saw before. There are no lone pairs, so the electron and molecule geometry would be the same. All right, so SO2, we did this one in the Lewis structure lesson. It has resonance if you did that part of the lesson. If not, it doesn't really matter. You'll get the same thing if you use either one of the resonance structures or the hybrid, right? So either way, this has 3 electron groups. It has an oxygen bond, and then a lone pair. So that makes the electron geometry trigonal planar, okay? But we can't see one of those, and so that makes our last group invisible, essentially, because there's no nucleus there, and so our molecule geometry will be bent. All right, so CH4, this will just look like this. The hydrogens, remember, won't have any lone pairs. That means we have 4 electron groups in this particular molecule, right? So our geometry is going to be tetrahedral. There's no extra lone pairs on the carbon, so it'll just be tetrahedral for both. Right, NH3. Here we have 3 hydrogens bonded to a nitrogen, and then we have a lone pair on the nitrogen too to complete its octet. All right, so that gives us 4 electron groups. So our electron geometry will be tetrahedral, but because we can't see one of those groups, that means our molecular geometry will be trigonal pyramidal, right? So this is the one that's not flat because it's got that lone pair on it. All right, and last but not least, we're going to do water. Water is H2O. The oxygen goes in the middle. It has 2 lone pairs. So those plus the 2 hydrogens will give us 4 electron groups. So that's an electron geometry of tetrahedral. And remember that if 2 of those groups we can't see, that gives us a bent with an angle of 109.5, or a little less than 109.5. All right, this is a great example of how the Lewis structure can give us all of the information about where the valence electrons are, but not give us accurate information about the shape. A lot of students would look at this Lewis structure and think this is linear. It is not, because it's got those two lone pairs that cause the angle to bend. Okay, so just keep that in mind.